I want you to take a second and just mentally deconstruct the physical journey you take during your morning commute.
Oh, that's a good exercise.
Right, because we usually just process it as a series of inconveniences.
Yeah.
Traffic, a bumpy road, maybe a really slow elevator.
Yeah, the stuff that gets in our way. Yeah.
Exactly. But I want you to look at the sheer, unforgiving physics of it all. You are hurtling 2 tons of metal down a highway off-ramp at like 60 miles an hour.
Which is terrifying when you really think about it.
It is. And that curve you're taking, it isn't arbitrary. It is a mathematically perfect transition curve designed specifically to balance the centripetal force against your tires.
Yep.
Or, you cross a suspension bridge just blissfully unaware of the immense dead loads and live loads being actively distributed through thousands of tons of steel cabling down into bedrock.
Just listening to a podcast, totally oblivious.
Totally oblivious. You walk into a skyscraper entirely blind to the three-dimensional labyrinth of high-voltage electrical conduits and pressurized water mains running mere inches behind the drywall. I mean, we entrust our lives to this infrastructure every single day, completely taking its structural perfection for granted.
It really is, it's an extraordinary act of collective trust.
Yeah.
And it functions seamlessly right up until the very microsecond it doesn't.
Right.
Because we exist entirely at the mercy of the structural integrity calculated by engineers, months or even years before a single cubic yard of concrete is ever poured.
Wow.
In civil engineering, gravity never takes a day off. And the materials we use, steel, concrete, asphalt, they just do not forgive mathematical rounding errors.
They really don't. And our mission for today's deep dive is to uncover the invisible digital scaffolding that guarantees that structural perfection. We are looking at the software that effectively allows us to simulate and test physical reality before it even exists.
It's fascinating stuff.
To do this, we are unpacking an incredibly comprehensive and technical text titled How AutoCAD Enhances Design Accuracy, Productivity, and Project Efficiency in Civil Engineering.
A very thorough guide.
Super thorough. And this resource was provided by Penn Content Digital. And for those of you who want to explore their deep reservoir of technical breakdowns, you can find them at www.penncontentdigital.info. It's really a foundational text that explains how modern engineering workflows operate, detailing that massive transition from the analog drafting board to what is now a highly sophisticated computational geometry engine.
And that transition is really the key to everything we are discussing today. Because in this field, as the text emphasizes, the margin for error is minimal.
Basically zero.
Effectively zero, yeah. What we're really exploring is the evolution of a singular software ecosystem. AutoCAD, which was developed by Autodesk, began decades ago as essentially a digital replacement for the T-square and the protractor.
Just drawing lines on a screen.
Exactly. But over time, it has evolved into this massive, interconnected, collaborative platform. It isn't just about rendering lines anymore. It's about processing the underlying mathematical relationships of physical objects.
To make sure everything is safe.
Right, to ensure that the built environment is both inherently safe and increasingly sustainable.
Okay, let's unpack this margin for error concept, because I think it's easy to conflate different types of design.
Oh, absolutely.
Like in graphic design or user interface design, a flaw in a digital file is an aesthetic or functional annoyance. A button doesn't work or a logo looks misaligned.
You refresh the page and fix it.
Right. But how is that margin fundamentally different on a computational level when we are talking about civil engineering and CAD?
Yeah.
Because the software isn't actually out there pouring the concrete.
No, it's not. But it's the difference between rendering pixels and defining a strict mathematical truth. In user interface design, your primary constraint is screen resolution and maybe human psychology. But in civil engineering, your primary constraint is the laws of thermodynamics, fluid dynamics, and material mechanics.
So the stakes are just slightly higher.
Just a bit. A flaw in an engineering drawing isn't a suggestion. It's a direct vector for catastrophic physical failure.
Wow.
Let's say a structural engineer is designing a steel connection for a roof truss. If the coordinate geometry in the CAD file is off by, say, half a degree,
Which is tiny.
microscopic,
Yeah.
but the steel fabricator cuts that beam exactly to that flawed specification. When it arrives on site, the bolt holes don't align.
And you can't just stretch steel.
Exactly. If they force it, they introduce unnatural shear stress into a joint that is supposed to be carrying a massive dead load. The text from Penn Content Digital is very deliberate in pointing this out. AutoCAD allows engineers to draft in 2D and 3D with absolute precision.
So it's not a picture.
No, we aren't talking about drawing a picture of a beam. We are defining a boundary representation, a mathematically precise 3D solid where every single vertex has an exact Cartesian coordinate.
So it's not just a digital pencil. It's more like a physics simulator, a sketchbook, and a safety inspector all rolled into one.
That's a great way to put it.
But here's my pushback on that. If the software has become this incredibly rigid, optimized physics simulator that handles all the heavy mathematical lifting, doesn't that inherently change the role of the human?
How do you mean?
Like, is the civil engineer still the actual designer at this point, or have they been reduced to, I don't know, a data entry clerk just feeding load parameters into a black box algorithm?
Ah, yeah. That is a highly debated topic within the industry right now. But the reality is that the software elevates the engineer's capability. It doesn't replace their intuition.
Elevates how?
AutoCAD handles what we call the deterministic mathematics. Before advanced CAD, an engineer would spend days manually calculating the moment of inertia for every single beam cross-section.
Doing the math by hand.
By hand, or using slide rules and early calculators to resolve complex systems of equations for load distributions. It was exhausting, it was highly prone to human error, and incredibly time-consuming.
I can't even imagine.
Right. But because AutoCAD natively handles that exact coordinate geometry and updates calculations instantly, it provides the cognitive bandwidth for actual engineering optimization.
Okay, so they aren't just doing arithmetic all day.
Exactly. The engineer is no longer bogged down asking, wait, did I carry the one in this equation? Instead, they are asking, if I alter the structural topology here, can I achieve the exact same shear strength using 20% less steel?
Oh, wow. So it's a strategic tool now.
Yes. It allows for rapid iteration and exploration of entirely new design paradigms that simply, well, they wouldn't have been feasible to calculate by hand.
So it's trading tedious arithmetic for high-level architectural and structural strategy. I can see how that fundamentally shifts the daily workflow. But to really grasp how it acts as this safety inspector and sketchbook, we have to look under the hood at the specific tools civil engineers use every day.
The core toolkit, right?
Yeah, the core toolkit. The Pen Content Digital Source outlines this, and the foundational element they highlight is layer management. Now, as someone who has dabbled in Photoshop, I know what a visual layer is.
Sure, most people do.
But in a complex civil engineering context, how does layer management actually function as a data organization tool rather than just, a way to hide things you don't want to look at?
What's fascinating here is that in AutoCAD, a layer is not just a transparent visual overlay.
Yeah.
It is a discrete array of object properties and metadata.
Metadata.
Yeah, so think about a modern commercial building. It might have tens of thousands of individual components. You have the structural steel, the reinforced concrete, the HVAC ductwork,
Not plumbing.
the plumbing supply, the high voltage electrical, the low voltage data cabling, the sanitary sewer lines.
That is a lot of stuff.
It's massive.
Yeah.
And if all of that geometry existed on a single data plane, it would just be a visually incomprehensible black mass of intersecting vectors on your screen.
Just a giant blob of lines.
Exactly. But more importantly, it would be computationally unwieldy to query. Layer management allows the engineer to segregate this data systematically.
Think of layer management like the transparent overlays in a medical anatomy book.
Oh, that's a perfect analogy.
Where you have the skeleton on one page and then you flip a transparent page to see the circulatory system
Yeah.
and another for the muscles.
Yes, and in AutoCAD, it's like object-oriented programming. You are assigning specific variables and inheritances to different classes of objects.
Right, so a layer has its own rules.
Precisely. You might have a layer dedicated solely to load-bearing concrete walls. Every line, arc, or 3D solid drawn on that layer automatically inherits a specific line weight, a specific line type, and crucially specific plot styles.
What do plot styles do?
They dictate how that object translates when it's exported to a fabrication machine or a contractor's tablet out in the field. And the engineer can freeze layers they aren't actively working on.
Like hiding the circulatory system to just look at the bones?
Exactly. But freezing doesn't just hide the visual representation. It actually removes those objects from the software's active memory regeneration cycle.
Oh, so it speeds up the computer.
Drastically. It improves the computing performance when navigating massive multi-gigabyte models. You can isolate the mechanical layer to see exactly where a duct runs, without the software having to constantly recalculate the visual geometry of the 1,000 structural bolts sitting 3 feet away.
That makes total sense from a data processing standpoint. It keeps the computer from just choking on its own geometry.
Exactly.
But let's look at another feature the text heavily emphasizes, which is dynamic blocks. The concept is that you have a reusable component that can change size and shape without being redrawn.
They are massive time savers.
Right. But if I'm an architect or a structural engineer and I need 50 different doors in a building, I don't draw 50 doors. I just pull like a digital Lego piece and stretch it.
That's the basic idea, yeah.
But doesn't relying on reusable parametric blocks risk making the built environment hyper-standardized? Does it strip the bespoke engineering out of the project and leave us with these rigid, cookie-cutter designs?
It's a completely understandable concern, but you have to separate the aesthetic design of a building from the functional mechanics of its infrastructure.
Okay, fair.
Dynamic blocks are generally applied to the latter. A dynamic block isn't just a static picture that you stretch. It is a collection of geometry bound by parametric constraints.
Meaning there's math involved.
Always.
Hmm.
Let's take a standard underground utility vault for a water main. The dynamic block for that vault contains strict mathematical rules. The walls must always remain parallel. The access hatch must always be perfectly centered.
So you can't accidentally put the hatch in the corner.
Right. And the concrete thickness must increase proportionally if the overall volume increases.
So the block itself has built-in engineering logic.
Exactly. When the engineer drops that block into the site plan, they can stretch it to fit a specific trench width, and the block automatically resolves its internal geometry to maintain structural compliance based on those parametric rules.
That's incredibly smart.
It is. And this does not stifle creativity. It eliminates redundant, error-prone manual labor. I mean, why would a highly trained civil engineer waste 6 hours manually redrawing the exact same fire hydrant, manhole cover, or standard I-beam connection 100 different times across a site plan?
They shouldn't. That sounds awful.
Right. By utilizing these parametrically controlled blocks, the engineer ensures absolute compliance with municipal codes and frees up their schedule to tackle the truly unique, bespoke challenges of the project.
Like the stuff that actually requires human problem solving.
Exactly. Like designing a custom retaining wall for an unpredictable, unstable soil slope on the edge of the property. You want their brainpower focused there, not on redrawing standard utility covers.
I see. You don't want a creative interpretation of a high-pressure gas valve.
Definitely not.
You want the exact, mathematically proven, universally compliant standard. And that directly feeds into the broader concept of minimizing catastrophic errors. The Pen Content Digital Text explicitly points to a trifecta of value, which is accuracy, productivity, and standardization.
The 3 pillars of modern CAD.
Right. And I want to drill down into accuracy. We've talked about precision, but how does the software actively enforce it? The text mentions tools like object snaps and polar tracking.
Oh, these are essential.
But from a computational standpoint, what are these tools actually doing when an engineer moves a mouse across a screen?
This is where we get into the computational geometry engine that really drives the software. When you are drawing on an analog drafting board, making 2 lines intersect perfectly at their endpoints relies entirely on human vision.
And having a really steady hand.
Right, the physical steadiness of your hand. You might be off by a fraction of a millimeter. On paper, that looks totally fine.
Nobody would notice.
But AutoCAD operates on a Cartesian coordinate system with double precision floating point format.
Whoa, okay, that sounds intense.
It just means it calculates positions out to 14 or 15 decimal places. If those 2 lines don't mathematically intersect in the database, the design is flawed.
Okay, here's where it gets really interesting. Because to you and me, a millimeter on a blueprint seems negligible. But I want you, the listener, to scale that up. Imagine trying to perfectly align 2 massive bridge segments meeting in the middle of a river.
Like the Golden Gate.
Exactly. If the angle of a structural cable is drafted manually and is off by 1/100 of a degree at the anchoring tower, by the time that line extends hundreds of feet down to the bridge deck,
that geometric error has compounded into a massive misalignment.
the steel connection literally won't fit. So object snaps and polar tracking ensure the digital math is flawless before a single piece of steel is cut. But how does the software actually execute that snap? Like, what is it doing?
When an engineer activates an object snap, or an OSNAP as we call them, they're turning on a background algorithm. This algorithm constantly queries the geometric data of the objects near the cursor. If the engineer wants to draw a line starting exactly from the midpoint of an existing steel beam, they don't eyeball it. As their cursor approaches the beam, the software calculates the exact mathematical midpoint of that vector based on its start and end coordinates.
It's doing the math in real time.
Instantly. And then it generates a localized magnetic bounding box around that midpoint.
So it's like a magnet.
Exactly. The moment the cursor enters that bounding box, the software overrides the human's mouth input and locks the cursor's coordinates precisely to that calculated midpoint.
It effectively removes the analog human jitter from the equation.
Yes. And polar tracking works similarly for angles. Instead of freehanding a rotation, the engineer sets the software to lock on to specific angular increments based on the coordinate system.
So you know it's exactly 90 degrees.
Right. This means orthogonal lines are perfectly parallel or perpendicular at a mathematical level. And this absolute geometric certainty is what allows the automated error checking features to function.
Which the pen content digital source mentions are crucial for avoiding costly delays or safety hazards.
Absolutely. Before design is ever finalized, the software can run interference checks, or what we call clash detection. It analyzes the 3D boundary representations of every object to see if any two solids occupy the same physical space.
Because two things can't exist in the same place at the same time.
Right, basic physics. Catching that a plumbing pipe intersects a load-bearing steel beam in the digital model saves tens of thousands of dollars and weeks of delays.
Compared to discovering that clash on the physical construction site with a crane waiting.
Exactly. It's a massive financial and safety safeguard.
And catching those clashes early brings us to the second and third pillars of that trifecta: productivity and standardization. The text touches on scripts and macros automating routine tasks. I know from my own experience with coding that scripting is powerful, but in an engineering context, I'm assuming we're talking about something far more robust than a simple keyboard shortcut.
Oh, much more robust. We are talking about utilizing programming languages, specifically AutoISP or Python, to directly manipulate the AutoCAD database.
Okay, give me an example of what that looks like.
An engineer can write a script that says, select all closed polylines on the property boundary layer, calculate their individual square footages, sum the total area, divide by the maximum allowable impervious surface ratio dictated by municipal code, and generate a formatted text table with the results in the corner of the drawing.
That is incredibly specific.
And what would take a human 2 hours of meticulous clicking, measuring, and calculator work is executed by the script in milliseconds.
That is an incredible productivity boost. But I want to introduce a different angle here because I think there's a psychological benefit to this automation.
Oh, absolutely.
We always talk about automation in terms of saving money or meeting deadlines, but isn't there a profound human safety element to this?
How so?
Well, if I'm an engineer and I've been staring at a grid of hundreds of rebar placements for 9 hours straight, I am going to experience severe decision fatigue.
Your brain just turns to mush.
Right. My brain gets tired and I'm going to make a mistake. By offloading that repetitive, standardized task to a Python script, does the software effectively act as a safeguard against human cognitive exhaustion?
That is a phenomenal insight, and it is a critical, often understated reality of modern engineering. Cognitive fatigue is one of the leading causes of design errors in any highly technical field.
Because we're human.
Exactly. When an engineer is forced to manually execute highly repetitive, intensely detailed tasks like dimensioning 100 identical column grids, their focus degrades. And that is precisely when a critical structural detail is accidentally overlooked.
Which is when bridges fail.
Right. When AutoCAD scripting and parametric standardization enforce the rules automatically, it acts as an ergonomic support system for the human brain. The engineer's cognitive energy is preserved for the high-level, complex problem-solving that a computer cannot do.
Like evaluating the whole building.
Like evaluating the holistic structural integrity of building against an unpredictable seismic event.
Wow. It preserves the human for the task that required genuine human intuition. That is a powerful way to frame it. But, no engineering project is a solo endeavor.
Oh, definitely not. It's a massive team effort.
Right. A major infrastructure project requires a sprawling ecosystem of specialists. You have the lead architect, the structural engineers, the geotechnical engineers analyzing the dirt, the MEP team handling mechanical, electrical, and plumbing.
He's an army of specialists.
And historically, this meant a nightmare of physical blueprints being mailed across the country, overlaid on light tables, covered in red ink, and mailed back. So how do all these highly accurate, standardized digital files move from a single computer to a massive team of builders today?
That's where the digital workflow comes in.
Right, the cloud collaboration and BIM integration mentioned in the pen content digital text. How has that fundamentally altered how these disparate teams interact? Because it can't just be a glorified Dropbox folder.
No, it is light years beyond a simple file sharing system. If we connect this to the bigger picture, the era of mailing physical blueprints is totally dead. We're looking at the transition from isolated CAD files to building information modeling, or BIM. Building information modeling. Okay, sectioning off geometry into layers was the first step. But BIM integration turns the entire project into a unified relational database.
So everything is interconnected.
Yes. In a traditional workflow, an architect draws a wall, and it's just two parallel lines on a screen. In a BIM-integrated AutoCAD environment, that wall is an intelligent 3D object.
Intelligent how?
The database knows exactly what material it is made of, what its thermal resistance rating is, and its exact mass.
Okay, so if the structural engineer logs into the cloud and decides that specific load-bearing wall needs to be moved 2 feet to the left to support a newly designed roof truss, what happens?
In the old days.
Yeah, in the old days, they'd make the change, issue a new revision, and pray the HVAC team noticed the update before they designed their ventilation ducts to run straight through the new wall location.
Exactly, the dreaded domino effect of design changes. But in a cloud-based, real-time BIM environment, the structural engineer moves that intelligent wall object in AutoCAD. Because the metadata is inherently tied to the geometry, that change propagates across the entire central database instantly. Instantly. The MEP engineer, working simultaneously from an office 3 states away, immediately sees the wall shift on their monitor.
Oh, wow.
Furthermore, the software's active clash detection algorithm instantly flags the new conflict, throwing an alert that says, structural wall object 452 now intersects at HVAC duct object 89.
It catches the mistake for them.
The conflict is identified and resolved in the digital space in real time, weeks before any physical materials are even ordered.
That's incredible. It's essentially object-oriented programming for concrete and steel. And the source also highlights version control, which I think a lot of people outside of software development misunderstand.
They think it's just hitting save as.
Right, just saving final draft v2.dwg on your desktop. But it isn't just a backup system. It's a highly granular tracking of every delta, every minute change made to the database, right?
Correct.
So think of it like a time machine for mistakes. If a new design iteration completely ruins the flow of a project, say an architectural firm tries a radical new layout for a hospital wing, and 2 weeks later the fire marshal reviews it and says the egress routes violate safety codes.
A nightmare scenario.
Right, but you don't have to manually undraft 2 weeks of work, you just rewind the timeline.
Precisely. Robust version control maintains a comprehensive navigable history of the project's evolution.
Yeah.
It logs exactly who made what change, at what exact coordinate, and at what time.
It's a perfect paper trail.
Yes. If a design iteration proves unviable, the team can revert the database to the exact state it was in on a specific Tuesday at 2:00 p.m. But beyond just acting as a failsafe, this cloud-based real-time collaboration completely democratizes engineering talent.
What do you mean by democratizes?
Historically, the speed of a project was bottlenecked by physical proximity. Today, a master hydrologist based in the Netherlands can perform complex drainage simulations on a site model, while a site developer in California simultaneously updates the subterranean topography based on fresh core samples.
They're working on the exact same model at the same time.
Manipulating the same digital truth simultaneously. It virtually eliminates the latency and miscommunication that historically plagued massive international joint ventures.
It is genuinely staggering how much critical communication is happening entirely through the shared geometry of the database without a single email needing to be sent.
It's silent collaboration.
So true. Now, we've talked a lot about the digital theory, the data structures, and the cloud architecture. And I want to bring this out of the server rack and into the dirt.
Let's get our boots muddy.
Exactly.
Yeah.
I want to ask, what does this actually look like when it hits the physical world? The Pen Content Digital Text breaks this down into real-world applications across various disciplines. Let's start with roads and highways. To the average driver, a highway is just a long, flat ribbon of asphalt. But geometrically, it has to be one of the most complex, continuous surfaces we build.
It absolutely is. A highway is a dynamic, three-dimensional corridor. Civil engineers use specialized vertical toolsets within AutoCAD, like Civil 3D, to handle precise alignment and profiling.
So it's not just a flat line.
Not at all. When you design a road, you are dealing with horizontal curves, vertical crests and sags, and complex super elevations.
Wait, let's define super elevation for the listener, because that goes back to the physics of my morning commute analogy from earlier.
Right. Super elevation is the banking of the roadway along a horizontal curve.
Like a NASCAR track, but less extreme.
Exactly. If a highway off-ramp was perfectly flat, the centrifugal force of a car taking that turn at speed would push it off the outside edge of the asphalt.
And you'd crash.
Right. The engineer has to calculate the exact degree to tilt the entire road surface inward to safely counter that outward force based on the design speed of the curve. And that tilt has to transition smoothly.
From the flat, straight away.
Exactly. It has to transition smoothly from the flat straightaway into the curve, which involves complex mathematical spirals called clothoids.
Wow.
AutoCAD processes all of this dynamically. If the engineer changes the design speed of the road from 50 to 65 miles per hour, the software automatically recalculates and adjusts the 3D geometry of the entire super elevation transition zone.
That is wild. And on top of that, you have to account for where the rainwater goes, right? The Penn Content digital source specifically notes analyzing drainage and grading.
Yes, water is the mortal enemy of infrastructure. A road must be crowned in the center or cross-sloped to shed water rapidly.
So it's slightly peaked in the middle.
Yes. AutoCAD allows the engineer to simulate the exact topography of the road surface and run fluid dynamic analyses.
To see where the water flows.
Right, to ensure that during a 100-year storm event, water will sheet flow to the catch basins rather than pooling in the travel lanes and causing hydroplaning.
Okay, let's pivot to bridges.
Hmm.
Because if water is the enemy of a road, gravity and wind are the ultimate adversaries of a bridge.
Without a doubt.
The text highlights structural analysis for integrity, but also the production of detailed fabrication and assembly drawings. I imagine the CAD requirements for a bridge are vastly different from a highway.
They are entirely different. A bridge requires incredibly intricate detailing. AutoCAD is often integrated with finite element analysis, or FEA software.
FEA, okay.
The engineer models the bridge's 3D geometry in CAD, and the FEA software meshes that geometry into thousands of tiny mathematical elements. It then simulates the application of physical forces.
Like the weight of the cars.
The dead load of the concrete, the live load of rush hour traffic, the harmonic resonance caused by gale force winds.
It simulates the exact bending and shear stresses on every individual steel member.
Correct. And once the macroscopic structural design is validated, AutoCAD is used for the microscopic reality of actually building it. We are talking about generating shop drawings for the steel fabricators.
Because you don't just forge a bridge in a river.
Exactly. A bridge isn't built on site. It is assembled on site from massive pieces manufactured in a factory. AutoCAD generates the exact blueprints that tell a CNC plasma cutter exactly where to slice a 2-inch thick steel plate and exactly where to drill the 50 holes for a specific gusset plate connection.
And if that's wrong?
If that CAD file's wrong, a multi-ton piece of steel arrives at the bridge site and simply cannot be attached.
Which brings a multi-million-dollar project to a grinding halt.
Exactly.
Moving on to buildings and infrastructure. The text emphasizes architectural floor plans, elevations, but heavily leans into modeling structural elements for safety and compliance. And for infrastructure, it mentions utility layout and site development.
The underground stuff.
Yes, I want to linger on utility layout because it is so entirely invisible to us. I want you to think about the last time you saw a massive construction site. Before the foundation is poured, it is a staggering, chaotic web of subterranean infrastructure. The water pipes, the gas lines, the electrical grid. It's an invisible three-dimensional puzzle beneath the dirt.
The subterranean realm is often the most complex part of site development. You have portable water mains, sanitary sewers, storm drains, natural gas lines, and massive concrete duct banks carrying fiber optics and power.
It's like a whole city underground.
It is. AutoCAD is used to create a comprehensive topological map of this underground world. The software tracks not just the X and Y coordinates of where a pipe runs, but its precise Z-axis elevation.
Depth.
Right, because gravity-fed systems, like sewer lines, require a very specific continuous downward slope to function.
Because AutoCAD is so versatile, does it act as the universal language between the architect designing the building's look and the engineer ensuring the bridge doesn't collapse?
It absolutely does. It provides a unified platform where environmental impact, like site development, landscaping, and structural compliance, can be visualized together. You can't just bend a sewer line over a water main if it ruins the slope, because the physics of gravity simply won't allow it to work.
So AutoCAD acts as the ultimate conflict resolution tool.
It forces every discipline to speak the exact same spatial language.
It sounds like a perfect system. But let's step back from the idealized capabilities of the software. We know that in the real world, deploying technology this dense is fraught with friction.
Oh, there are always headaches.
Right, and the pen content digital source does not shy away from the pain points. And I want to dive into the realities of implementing these tools. The first major hurdle they identify is the steep learning curve. And frankly, given everything we've just discussed about coordinate geometry, parametric constraints, and database scripting, I'm surprised anyone masters it at all.
It is a monumental challenge. I mean, AutoCAD is not consumer software. It is highly specialized enterprise architecture. The user interface alone is intimidating, featuring hundreds of tool ribbons, command line interfaces, and property palettes.
It's not just point and click.
Not at all. A new graduate might understand the physics of a retaining wall perfectly, but translating that physics into compliant CAD geometry takes hundreds, if not thousands of hours of practice. Firms must invest heavily in ongoing structured training programs just to maintain a baseline of operational efficiency.
And that leads directly to the second challenge, the text highlights, which is complexity management.
The digital knot.
Yes. So what does this all mean? If you have all these layers, BIM integrations, and cloud collaborators throwing their data into this infinitely large digital sandbox, couldn't a massive project just become a totally unwieldy digital knot? How do firms prevent a file from just collapsing under its own complexity?
This raises an incredibly important question about the human discipline required to operate advanced technology. The software is infinitely capable, but it is entirely agnostic to bad habits.
It'll let you make a mess if you want to.
Exactly. If a firm does not enforce draconian protocols for data architecture, the project will absolutely collapse under its own bloat. We see this frequently with things like external references, or XREFs.
What is an external reference?
Instead of drawing every single detail in one massive, sluggish file, engineers use XREFs to link other drawings into their master file.
Oh, I see.
So the MEP engineer links the structural engineer's column layout into their file so they can route ductwork around it. But if strict file management isn't enforced, you can create circular references.
Like an infinite loop.
Yes. File A links to file B, which links to file C, which inadvertently links back to file A. When the software tries to load, it gets caught in an infinite loop of data regeneration and crashes the entire system.
Oh, wow. A literal digital knot.
Exactly. To mitigate this, the industry relies on incredibly strict, standardized frameworks, such as the National CAD Standard, the NCS, or the ISO 19650 protocols for information management.
So there are rules for the rules.
Yes. These frameworks dictate exact universal naming conventions for layers, files, and blocks. You don't get to name a layer mislines or Bob's Edits too.
Like casual naming.
No. A layer name looks like a line of code like C to POMINR, which universally tells any engineer in the world that this layer contains civil, topographical, minor contour lines. Without that rigorous standardization and consistent documentation, the tool becomes a liability rather than an asset.
It requires a level of organizational discipline that rivals the engineering itself.
It really does.
And just to ensure that no one ever gets comfortable, the text points out the persistent challenge of software updates. The underlying code base of the software is constantly shifting, right?
Constantly. Autodesk pushes updates that overhaul rendering engines, introduce new AI toolsets, or deprecate old commands. If an engineering firm isn't actively monitoring and adapting to these updates, their workflows become obsolete very quickly.
It forces a cultural shift within engineering firms, doesn't it?
Yes, you cannot rest on the knowledge you acquired in university. The steep learning curve and the constant influx of new software capabilities mandate a culture of continuous learning. An engineer's digital competency degrades rapidly if they are not actively upgrading their skills in tandem with the software.
It's a relentless arms race of digital proficiency.
That's a great way to describe it.
But conquering these present-day challenges is vital because, well, the technology is accelerating. We are not going back to drawing with graphite on vellum. So looking toward the horizon, the final section of the Pen Content Digital Text outlines the future trends in civil engineering.
And this is where it gets really sci-fi.
It really does.
Yeah.
They identify three massive shifts: AI integration, enhanced 3D capabilities, and a paramount focus on sustainability. Let's tackle the 3D aspect first. We've talked extensively about 3D models and boundary representations. What does enhanced capabilities actually imply? How much more 3D can it get?
It implies a shift from viewing a 3D model on a 2D monitor to true spatial computing.
Like VR.
Yes. We are rapidly approaching the seamless integration of AutoCAD models with augmented reality, AR, and virtual reality, VR environments.
Hmm.
Enhanced 3D capabilities won't just look pretty, they will likely be fully immersive environments.
So currently, an engineer rotates a model on a screen to check for clashes with a mouse.
Right. But in the near future, they will put on a headset and physically walk through a 1.1 scale holographic projection of a bridge or a subterranean pump station before any concrete is poured.
That is
They
mind-blowing.
will be able to look up and visually inspect the clearances of the HVAC ductwork, or look down and verify the routing of the rebar. It transforms the digital model from a mathematical abstraction into an immersive, experiential prototype.
I can easily envision a scenario where you bring, like, a city council member who has zero engineering background into a VR space. Instead of trying to explain a complex 2D topographical map to them, which they won't understand, you just let them walk down the holographic street and see exactly how the new retaining wall will look and function in their neighborhood.
It completely bridges the communication gap.
But it's the AI integration that truly fascinates me. The text notes that AI will automate even more complex tasks. We already discussed Python scripts automating area calculations. What is the next leap? Are we talking about AI actively participating in the structural physics?
We are talking about generative design and topology optimization.
Generative design.
Yes. Currently, an engineer uses AutoCAD to draw a specific design and then tests it to see if it works. With AI integration, the workflow reverses.
What do you mean?
The engineer will input the constraints into the software. They'll say, I need a structural beam that spans 50 feet, must support a live load of 20 tons, and cannot exceed a depth of 2 feet.
And then the AI just builds it.
The AI algorithm will rapidly iterate through thousands of geometric permutations, calculating the physics for each one, and present the engineer with the 10 most optimal, mathematically sound designs.
Wow.
And many of these designs will feature organic, complex geometries that a human mind would never naturally conceive.
So the software transitions from being a passive tool that simply records what the human draws into an active computational partner that suggests entirely novel solutions.
Exactly.
And if you tie that generative capability into the third trend, the focus on sustainability, the implications are massive.
They are deeply interconnected.
If AI is handling the complex tasks and the focus shifts to sustainability, does AutoCAD essentially become an active partner that suggests greener options? Like if I'm designing a bridge, could the software pop up and say, hey, your current design requires 5,000 tons of Portland cement, which has a massive carbon footprint. But if you use this eco-friendly material instead, and this AI-generated truss topology, you'll achieve the exact same shear strength while reducing your carbon emissions by 30%.
That is precisely the trajectory outlined in the pen content digital text. As climate change forces a reckoning in how we construct the built environment, sustainability can no longer be an afterthought.
It has to be baked in.
It must be a computable metric built into the very beginning of the design phase. The CAD software of the future won't just check for errors. It will actively synthesize structural physics, material science, and global environmental data. It will act as a real-time advocate for green engineering, providing the data necessary to make decisions that minimize ecological impact without compromising safety.
That is a staggering evolution. From a digital replacement for a pencil to an AI-driven engine actively optimizing the carbon footprint of human infrastructure.
It's come a very long way.
It really has. Okay, we have covered an immense amount of ground today. We started by exploring the unforgiving physics of the physical world, and we've drilled deep into how AutoCAD, through its precise coordinate geometry, its rigorous parametric constraints, and its cloud-based database architecture, allows engineers to mathematically simulate reality before building it.
Simulating truth.
Yes. We've seen how tools from object snaps to complex scripting preserve an engineer's cognitive bandwidth, preventing catastrophic errors. And we've seen how this unified digital language allows teams across the globe to collaborate instantly, building everything from perfectly banked highway curves to deep subterranean utility webs.
It truly is the definitive mechanism that allows our modern, highly engineered world to exist safely.
Exactly. So
Yeah.
tomorrow, when you take that morning commute, when you walk across a plaza or drive over an overpass, I want you to look at the concrete and steel and recognize the invisible, mathematically perfect digital scaffolding that preceded it. It is a testament to the continuous evolution of engineering technology, meticulously detailed in resources like the one provided by Pen Content Digital.
It's all hidden right in plain sight.
It really is. But before we sign off, I want to leave you with one final lingering question to ponder regarding the future we just explored. If the integration of artificial intelligence and generative design continues to accelerate, if the software itself takes over the heavy lifting of calculating optimal load distributions, running exhaustive fluid dynamics simulations, and autonomously selecting the most sustainable materials, how will the fundamental role of the human civil engineer change over the next few decades?
That is the big question.
Right. If the digital system eventually knows exactly how to build something perfectly, safely, and efficiently, will the human engineer's job shift entirely from calculating the math to simply dreaming up what we should build next? As our invisible scaffolding gets infinitely smarter, the ultimate question may no longer be how we build our world, but what kind of world we want to ask it to build.